Good day everyone. We are Group 8 and today we will tackle about concepts of chemical bonding. I am Reina Eliza P. Pineda. First slide, chemical bonds. Three basic types of bonds. First, ionic, electrostatic attraction between ions. This type of bond, which is linkage from the electrostatic attraction between oppositely charged ions in a chemical compound. So next is covalent, sharing electrons. The interatomic linkage that results from the sharing of an electron pair between two atoms. So next is metallic, metals atoms bonded by free electrons. This is the force that holds atoms together in a metallic substance. Next slide. Lewis symbol. For an element consists of the element's chemical symbol plus a dot for each valence electron. When forming compounds, atoms tend to gain, lose, or share electrons until they are surrounded by 8 valence electrons, or we all know the octet rule. Energetics of ionic bonding. As we saw in the last chapter, it takes 495 kJ/mole to remove electrons from sodium. We get 349 kJ/mole back by giving electrons to chlorine. So we can see in the slides or the PowerPoint that the sodium gives 1 dot to chlorine, so it make 8 dots. So it complete the octet rule. So next is energetics ionic bonding. But these numbers don't explain why the reaction of sodium metal and chlorine gas to form sodium chloride is so exothermic. So dito sinasabi na hindi daw kayang i-explain yung reaction ng sodium metal and chlorine gas para mag-form siya ng sodium chloride. So, yan po. Next is, what is as yet unaccounted for is the electrostatic attraction between the newly formed sodium cation and chloride anion. So, next po. Born-Haber cycle. By accounting for enthalpy of formation, sublimation, bond dissociation, ionization, energy, electron affinity, we can determine lattice energy. Application of Hess law. It takes energy to convert the elements to atoms or endothermic. It takes energy to create a cation, or energy is released by making the anion exothermic. The next is the formation of the solid from gaseous ions releases a large amount of energy, exothermic. The reverse process requires a large amount of energy, endothermic. Lattice energy. The energy required to completely separate a mole of a solid ionic compound into gaseous ions. Sample, NaCl dash to Na plus close parenthesis G plus Cl negative close parenthesis G. So AH lattice equals to plus 788 kJ/mole. The amount of energy is released to make the ionic compound in Born-Haber cycle. The energy associated with electrostatic interactions is governed by a equation. E, big letter E, and under this is EL equals to K Q1 Q2 over D, where K equals to 8.99 times 10 times 10 to 9th J minus M slash C2. Lattice energy is increases with the charge of the lattice energy increases with the charge on the ions and decreasing size of ions. Electron configurations of ions. Main group metals tend to stop losing electrons once they attain a noble gas configuration. Energy to remove electron from an inner shell is not compensated by lattice energy. Nonmetals gain electrons to form the electron configuration of the nearest noble gas. Example, Na 1s2, 2s2, 2p6, 3s1 equals to Ne3s1. Na plus 1s2, 2s2, 2p6 equals Ne. Cl or chlorine 1s2, 2s2, 2p6, 3s2, 3,5p equals to Ne3s2, 3,5p. Cl negative 1s2, 2s2, 2p6, 3s2, 3p6 equals to Ne 3s2, 3p6 equals Ar. Transition metals don't follow the octet rule. Transition metals lose Ns valence electrons with highest N first, then lose N negative 1 d electrons to attain the given charge. Write the electron configuration for Zn2 plus, M2, Mn2 plus, and Mn3 plus. So, yun pa. Thank you and thank you.
I'm Ergian Peralta. Covalent bonding. Bonds between nonmetals. In these bonds, atoms share electrons. H point plus point H to H double point H. There are several electrostatic interactions in these bonds. Attraction between electrons and nuclei. Repulsion between electrons. Repulsions between nuclei. Next po. Lewis structures. Lewis structures are representation of molecules showing all electrons bonding and non-bonding. Next. Lewis structures. The group number is the number of valence electrons. To get an octet like the nearest noble gas in the simple covalent molecules for nonmetals, the number of bonds needed will be the same as the electrons needed to complete the octet. Lone pairs. Electrons locate on only one atom in a Lewis structure. The second is bonding pairs. Shares electrons in the Lewis structures and can be represented by two dots or one line. Next po. Multiple bonds. Pairs is single bonds. Share only one pair of electrons. Second, double bonds. Share two pairs of electrons. And the last one is three bonds are shared between two atoms in triple bonds. Next po. Polarity of bonds. Electrons in a covalent bonds are always shared equally between two atoms. Bonds polarity is a measure of how equally or unequally the electrons in covalent bonds are shared. In a nonpolar covalent bonds, the electrons are shared equally. In a polar covalent bonds, one of the atoms attracts electrons to itself with a greater force. Next. Electronegativity. The ability of atoms in a molecule to attract electrons to itself. In the periodic table, electronegativity increases as you go from left to right across a row, from the bottom to the top of a column. Next po. Polar or nonpolar covalent bonds. The low electron density and high electron density. Although atoms often form compounds by sharing electrons, the electrons are always shared equally. The second is fluorine. has a greater attraction on the electrons it shares with hydrogen than hydrogen does. Therefore, the fluorine end of the molecule has more electron density than the hydrogen end in the HF molecule. Next one.
Is a bond covalent, polar covalent, or ionic? Simple approach. Metal plus nonmetal is ionic. Nonmetal plus nonmetal is covalent. However, this simple approach does take into account oxidation number of metal. Higher oxidation number can give covalent bonding. There is a continuum between the extremes of ionic and covalent bonding. Electronegativity difference can be used. Nonpolar covalent bond, polar covalent bond, ionic bond. Example, rank of the following bonds formed between atoms in the order of increasing polarity. Dipole. When two atoms share electron inequality, a bond dipole results. The dipole moment produced by two equal but opposite charges separated by a distance r is equal QR. The dipole moment is measured in device D. 1 dBi equals 3.34 x 10 negative 30 cm. Polar covalent bond. The greater the difference in electronegativity, the more polar is the bond. Example, calculate the partial charge on the HNF atoms in HF. Drawing Lewis structures. 1. Find the sum of all atoms in the polyatomic ion or molecule. If it is an anion, add 1 electron for each negative charge. If it is a cation, subtract of 1 electron of each positive charge. Number 2. The central atom is the least electronegative element that is hydrogen. Connect the outer atoms to it by single bonds. Number 3. Complete the octet of the outer atom. Number 4. Fill the octet of the central atom. Number 5. If you run out of electrons before the central atom, it has octet. Form multiply bonds until it does. Writing Lewis structure. Assign formal charge. For each atom, count the electron in lone pairs and half the electron it shares with other atoms. Subtract that form the number of valence electrons for the atom. The difference is its formal charge. The best Lewis structure. It's the one with the fewest charge. Put a negative charge on the most electronegative atom.
Writing Lewis structures. Find the sum of valence electrons of all atoms in polyatomic ion or molecule. If it is an action, add 1 electron for each negative charge. If it is a cation, subtract 1 electron for each positive charge. 2. The central atom is the least electronegative element that is hydrogen. Connect the other atoms to it by single bonds. 3. Fill the octets of the other atoms. 4. Fill the octet of the central atom. 5. If you run out of electrons before the central atom has an octet, from multiple bonds until it does. The assigned formal charges. For each atom, count the electron in lone pairs and half the electron it shares with other atoms. Subtract that form from the number of valence electron for that atom. The difference is its formal charge. The best Lewis structure is the one with the fewest charge. Puts negative charge on the most electronegative atom. Resonance. This is the Lewis structure we will draw for ozone O03. But this is the odds with the true observed structure of ozone O3 in which both 0 bonds are the same length, but other oxygen atoms have a charge of 1/2. Resonance. Resonance structures are Lewis structures that differ only with respect to placement of the electrons. One Lewis structure cannot accurately depict of a molecule such as ozone. We use multiply structure resonance structures to describe the molecule. Two identical bonds with a bond order equal 1.5403. Electrons not localized but rather are delocalized. Example, be able to determine how many, if any, resonance structure are exhibited by a molecule or polyatomic ion. A. Nitrate ion. B. Sulfur trioxide. Resonance. The organic compound benzene C6H6 has two resonance structure. It is commonly depicted as a hexagon with a circle inside to signify the delocalized electrons in the ring. Localized electrons are specifically on one atom or shared between two atoms. Delocalized electrons are shared by multiple atoms. Average formal change and average band order. Average formal change. Sum of formal charges on oxygen atoms as it appears in all resonance structures. Number of resonance structures. Average band order. Total number of bond between an atom pair as it appears in all resonance structures. Number of resonance structures sa baba. Average formal charge on oxygen 1/2. Average bond order. Expectation to octet rule. There are three types of ions or molecules that do not follow the octet rule. Ions or molecules with an odd number of electrons. Ions or molecule with less than an octet. Ions or molecules with more than an octet.
Fewer than an octet of electrons. Example, for boron trifluoride, draw Lewis structures in which number 1, the octet rule is obeyed. Number 2, the formal charges are minimized. Giving boron a field octet places a negative charge on the boron and a positive charge on fluorine. This would not be an accurate picture of the distribution of electrons in BF3. Therefore, structures that put a double bond between boron and fluorine are less important than the one that leaves boron with 6 valence electrons. Covalent bond strength. And this is the example. Cl-Cl gram to 2Cl gram. The strength of a bond is measured by determining how much energy is required to break the bond. This is the bond enthalpy. The bond dissociation enthalpy for a fluorine dash C bond. The Cl is 242 kJ per bond enthalpies. This table lists the average bond enthalpies for many different types of bonds. Average bond enthalpies are positive because bond breaking is an endothermic process. And this is the example. Example, using bond enthalpies from table 8.3. Estimate the enthalpy of the gas phase combustion reaction of methane. And this is the bond enthalpy and bond length. And you can see it on the screen. Bond length. Bond length. Table 8.4. Average bond lengths for some single, double, and triple bonds. Bond C to C. Bond length is 1.54. We can also measure an average bond length for different bond types. As the number of bonds between two atoms increases, the bond length decreases.